All right. So as chemists, naturally, we may want to synthesize carbohydrates ourselves, right? That way we can manipulate them, maybe do different stuff with them, and then see how they react, right? Make all new kinds of things, right? So what we need to be able to do is lengthen the chain. If we start from, a 1 or 2 carbon sugar, we want to be able to make it longer to make whatever kind of sugar we want, right? Generally, 5 and 6 carbon long sugars are more common. And so this is the Kilani Fisher synthesis. And so this will allow us to synthetically create carbohydrates, or at least lengthen them. And it has to do with the reaction that we've already learned. So for example, if we have this alkyl halide and we wanted to lengthen it, one thing we could do is attack this with a cyano group, a CN minus. Right, it'll do an SN2 reaction. Now we've got 1, 2, 3, 4 carbons long. Of course, cyano group, not that common. We just add some H3O plus, and in this case, it can be transformed into a carboxylic acid, but we have milder ways to do this and then stop at an aldehyde if that's what we want. But what you can see by doing this is we've added carbon number 4 on here. And that's basically what they do in this mechanism. You have your carbonyl, you add some HCN, which will attack that carbonyl, transform it into an alcohol, and then add that cyano group. Of course, you're going to get both enantiomers. This is not going to be an enantioselective position. After that, we can hydrolyze the cyano group to an imine. And then hydrolyze further either to an aldehyde, right? We don't want to go all the way to carboxylic acid because our sugars don't have carboxylic acids. And so what you can see is we've lengthened the chain. We've added another carbon to our sugar. So for example, if we had this guy, right, what we've got here is a pentose. It's got 5 carbons, right? 1, 2, 3, 4, 5. And of course, they figured out how to do it with milder reagents. So in the first step, you add HCN, which we've seen that's relatively simple. Then after that, you do some hydrogen on palladium. That way you can reduce it. And then you add some barium sulfate to this as well, and some water to help lightly hydrolyze it. And so then what you'll get, you'll add on your extra carbon. Note that the stereochemistry of all the other carbons remains unchanged, right? So we have the OH there, and then OH there, H, H, H. And now we'll end up with 1 extra carbon, right? Where this carbon right now has become this one right here. And then this carbon right here came from our cyano group. The alcohol came from the water that the oxygen came from the water that hydrolyzed it. Of course, you're going to get both enantiomers. This is not going to be an enantioselective position, but again, it's only going to be that top stereocenter that you're going to get a mixture of, right? The rest of the stereocenters will remain untouched. And you can see why they have different types of notation in biochemistry, because these things are just such a pain to draw a lot of. So this one right here would be D-glucose. Again, you don't have to know that, but if you want to know it, there it is. Again, this carbon was added. In this case, these are not enantiomers because only one of them, only one of the stereocenters is different. So this would not, on the right, would not be L-glucose or anything like this. This one right here would be D-mannose. And of course, the relationship between these two is some of our stereocenters stayed the same, some of those changed. That's the definition of a diastereomer. And of course, we start off with a pentose, so we end up here with a hexose afterwards.